Hey guys, it's Mr. Sheeline here. This is just going to be a run through of going through the position time graphs in case you were absent, because we did pretty much practice this just in class. So this is just to pretty much run through what you would have seen in class. We're gonna kind of put this together, walk through here of how to read position time graphs, and then also how to we'll get to learning how to put one together ourselves in the future. But for now, I guess it'll just be for uh, reading them and interpreting them. So here we've got an example of a position time graph. As the name basically lays out, a position time graph is just a graph where it's relating the position and the time of a particular object while it's in motion. So what is the thing that, or I guess maybe instead we'll actually just walk through, and instead of having it like this, I'm going to have it open like so. And here, let me just do this F11, so we got full screen. So I guess as up at the top, we've been working. It should say we have been working with the calculations of speed. And velocity using the formula, and also that magic triangle that's in the notes that we use both for speed and velocity. And then we're going to be looking at the graphs of position and time and how they relate with velocity, because it is an important thing to understand, or at least know that it exists, and how to interpret it and all that good stuff. Okay, so looking at the graph in the bottom corner, so looking at this guy right here. Looking at this, what is on the x-axis? So looking at it, what is on the x-axis, and like this reminder here, what is on it? So we've got the horizontal, what's on the x-axis. Of course, this is going to be our x-axis. So, and easy enough, position time, we remember that usually in our title, we include both the y and also x-axis variables, which is our independent variable and our dependent variable over here, independent variable down here, and it should be pretty obvious which one is which. So looking at the graph at the bottom, what is on our x-axis? Easy peasy. Time, specifically time of day. Okay, because look, they're measuring from 9 a.m. to 9:30 to 10 to 10:30, 11 to 11:30. So it's a time of day. Does it say if it's in the morning or the evening? No. Should it? Maybe, depending on the particular, motion, and if it really matters, if it's, night or day, if you're trying to set a scene. But for all intents and purposes, practicing right now, it doesn't really matter. So time of day is on the x-axis. So what's on the y-axis? Easy peasy. Looking at our y-axis here, it says distance. We're working with velocity. So you could say position, you can say distance. Really? Displacement or position is really what it should be. Displacement's the more accurate one here, since we are determining the velocity using these graphs. And if you're wondering, yes, you can figure out speed using these graphs as well. But anyway, we're just focusing on velocity. So as the day, number 3 here, as the day goes on, what happens to the distance from school? So does it increase? Does it decrease? Does it stay the same? So reading this guy, looking at it, this is that interpreting part. So looking at it, we're starting here at 0 on the y-axis. So this is how far you're moving away from your original position. Or at least, this is our original position. And when we deviate, when we move away from that position, that's where our graph is going to increase or decrease depending if we're moving in a positive direction or a negative direction. So it looks like here, looking at here, let's try to read this. So let's just see where it increases. Let's see where it decreases. Let's see where it stays the same. So if we start down here at 9 o'clock, we haven't moved. Notice that as time goes on, notice that as we move on the horizontal, we have an increase in distance or displacement from our original position. So it looks like from 9 o'clock to about 10 o'clock, it looks like we have moved 50 miles. So they're moving probably in a car, because walking 50 miles in 2 hours, that's a pretty good jogging pace, but anyway, maybe it is jogging, who knows. But anyway, so looks like in 2 hours we've moved 50 miles. Okay, cool. What about this space right here? So we've got 10 to 10:30. So looking at it, so if this from here to here means, we've gone up in displacement, we've gone farther away in the positive direction, whichever one that's been established. The positive direction, we have moved 50 miles in 2 hours. Okay. So that you could say that's a velocity of 25 miles, per hour. Okay. In whatever this direction is, we'll say forward. What about right here? What do we think is happening here? So we increase. We had an increase in the displacement with an increase in time, but now we've got a stagnation. Now we have time is moving, it's going forward, but there is no change in position. What does that mean? So it must mean that for a half hour, someone stopped somewhere. We have no change in position. So that should tell you that in this case, someone had to take a break. Maybe they stopped for lunch. Maybe they stopped for brunch. They stopped somewhere for half an hour. And then we can see here after that half hour is up, they travel go from 50 to 90. They go from 50 miles to 90 miles in an hour. So, and it looks like, looking at the difference between this angle and this angle, it looks like they went a slightly slower. It was a slightly slower rate. You can kind of see if you look at from this point to this point and try to compare it to this point to this point, you can see that this guy, the angle is a little, it's a little lower. So that should tell you, oh, they slowed down. They didn't go as fast as they did right here. So as the day goes on, what's happening with the distance from the school? We'll say displacement. I'll change that on your guys' version. It'll say displacement. So as the day goes on, what happens to the displacement? Well, we could say during the day, or as the day goes on, we could say, well, displacement has increased, or we'll say displacement increased for the first 2 hours. No change in displacement for half an hour. It'll actually say displacement increased for the first 2 hours at a constant rate. No change in displacement for an hour and a half. And we'll say displacement then increased again for another hour at a constant rate. So the constant rate is pretty important. I'm going to be doing here. I'll do this. The constant rate thing is an important distinction. It's an important idea to have here. Okay. It's an important idea to have here specifically because we can see here, this is a very straight line. That says that we're moving at a constant velocity. We are not changing our speed, we're not changing the rate of our velocity. In this case, from 9 o'clock to 10 o'clock and I think I said 2 hours, but I should have said 2 hours. That's just 1 hour. Sorry. I know I said, and then I even wrote it for the first hour. Oops, I just realized that. First hour, it's a constant rate. We have constant velocity here. Okay, we have a constant velocity. We didn't have a change in direction. We didn't have a change in the rate. It is constant, which is it's an important thing to mark on. Okay, here there's also, there is a change in velocity. Technically, though, or I shouldn't say there's no technically. Here it's a change in velocity, but there's no change in displacement. So there's no velocity here. They're staying in one spot. And then they start getting going again in the same direction as this guy, just a little slower, but still constant velocity. Okay. Try to think to yourself, because we'll work with it a little bit. Try to think to yourself, what would it look like if we had a change in velocity? What would that look like on a graph here Would it look, would it go up and then down and then up again? Would it zigzag? Would it be curved? Would it be, what would it look like? Maybe try to put that together yourself. Try to work that out on your own. We'll get to that on a later date and practice it just a little bit. For now, we just want to focus on these super duper simple graphs. So anyway, and then I'm going to also change this. So based on the formula you asked that you used last week, velocity is equal to displacement over time. If this graph shows distance over time, displacement over time on the axes, what do you think the line shows? So it should be pretty apparent now because I've pretty much given this away, but think about it. So you've got distance, this is distance and time, and we're working with velocity. We've been working with speed. What is speed and velocity? It's the amount of the length in which you traveled over a particular time. And using those two, we find, for the most part, on average, how quickly the rate in which you moved in this particular kind of measurement over this particular measurement of time. So based on the formula, what do you think this is? So we've got displacement, we got time, pretty much the only thing left over here. Oh, well, the line shows us velocity. Okay. So again, from here to here, so from 9 to 10 p.m., we traveled 1 hour, or we traveled 50 miles in 1 hour. So what does that tell you? If we traveled 50 miles in 1 hour, we were moving at a rate, we were moving with a velocity of 50 miles per hour, and we'll say forward. Well, what was your velocity from 10 to 10:30? There's no change in position. Time has moved, but if you have no displacement, you don't have velocity. So here, there is no velocity. It's zero. Velocity is zero. Okay. But then you've got from here to here, we're moving from 50 to 90. So we move 40 miles, and we move 40 miles in an hour. So how quickly were we going here? At what constant rate? Well, we were moving at 40 miles an hour forward from here to here. Okay. And that's pretty much a position time graph. And here's the same graph, just kind of blown up a little bigger. And I love how it's really doing wonders to the color on my face here. But anyway, so here we've got the same graph, just enhanced in case you need it enhanced to take a better look at it. But anyway, that's what we've been working with here. All it is you're looking at, okay, what's the time difference between each of these points? How does this matter with the displacement? And how can we read that to tell the rate, the velocity in which something was moving in these graphs? So what you're going to do here is that basically you're just going to be reading these graphs here. So here you've got practice with position time graphs for Emma. So Emma traveled to her grandmother's house and back. The distance, the position time graph, the position time graph shows information about her journey. Okay, and you're just answering questions. So you're looking at these little points, you're reading the time, you're reading the displacement, and you're trying to make sense of what happened. How quickly did Emma move? When did she move? When didn't she move? And you're interpreting the graph. And you'll be doing the same thing here with the train. Okay, so a train travels from Milton to Redville, stops for 30 minutes, then travels to Leek. So here you are just answering questions using this graph here, making sense of position time graphs. Okay, it's an important concept to understand. It's an important concept to practice. If you guys have any questions, make sure you get a hold of me. We worked on this in class, and I know this, if you're watching this and you're absent, I know this kind of sucks because I can't really be there to help you out terribly. So if there's something you don't understand, make sure you get a hold of me. Text me on Remind. Email me, get a hold of me on Google Classroom, whatever it is you need to do to talk to me about whatever help you need with these particular graphs. So that's what we did today. And again, if you got questions, get a hold of me. If not, then I'll see you guys in the next one. Oh, and cool. You get to see me just for a little bit longer because my toolbar doesn't want to work. So that's cool. So, all right, guys, I'll see you in the next one.